Yeah, welcome again, everyone. So we are starting the workshop. This is the first talk by Peter Rakich from Yale University. Peter is the Dubinsky Professor of Applied Physics. Is that how it pronounces? Okay. Yeah, and he works on a lot of different things, including nonlinear optics, integrated photonics, optomechanics, and the stuff. So back when I was doing my PhD at Columbia, we were doing microwave generation using photonic platform. Our favorite platform was silicon nitride, which we tried very hard to squeeze every bit of stability out of it. And then Peter came in and demonstrated their amazing new platform of microresonators that just blew us out of the water. So yeah, today I think you will hear a part of it. And also, Peter, I guess you recently got a Roberts fund that's related to the work, and you also started the startup, right? Right. Okay, cool. Yeah. Can't wait to hear about it. Go.
Thank you. And thanks so much to the organizers. This is a really fun, topic. It can be lonely to be doing crazy things with cavities without a community to share the enthusiasm. So this is great. So what I'll tell you about, I abbreviated my title. I'll tell you about phonons and noise, how we're using cavities to try to control or shape both. And maybe just a bit about the sort of things that we do in the group, and maybe a story and outline, an outline in pictures here. So my group historically does nonlinear optics and integrated photonics. So where I'm going to start in this discussion is some maybe 10 years ago started working on studying cryogenic phonon physics. How long can phonons live? Can we make a resonator that will hold those phonons for a long time to make a quantum memory? And from fabrication techniques we developed to make these acoustic resonators, we realized, well, we can also start making optical Fabry-Perot resonators using the same techniques. And I'll tell you about some of these new mirrors we've developed, as well as new types of cavities that are, to make really compact vacuum gap reference cavities. So that's what some of these things are. So I'll tell you about our efforts to, do some science and develop some new technologies there, integrating them into different systems. So as a starting point, I'll tell you about the acoustics. This is kind of how things started. So a long time ago, we were, trying to understand some aspects of phonon physics and how good of a solid state quantum memory can we make with a phonon. This is what started us working on making Fabry-Perots for high frequency phonons, sort of tens of gigahertz thinking here. We've coupled them to superconducting qubits with Yuan Chu, who's now doing great things along those lines at ETH. But what I'll tell you about today are efforts to control or manipulate these phonons with light. So that involves an optical Fabry-Perot resonator and an acoustic Fabry-Perot resonator. But to start out, I'm going to tell you a little bit about the spectroscopy and development of these resonators. And if not all of you are familiar with cavity optomechanics, this is my really, really simple primer. You can think of, the objective of cavity optomechanics is maybe in some context, quantum control of phonons with light. And as a simple starting point to understand this is to think of a canonical mass spring system that might be a mirror on a spring. And if we have a laser beam that impinges on it, as it vibrates, you're going to have two sidebands. In a quantum picture, you can think of the blue sideband as being an anti-Stokes process where you're annihilating a phonon and upconverting it, or the red sideband being the Stokes process where you're contributing a phonon with each scattered photon. So if you're trying to control which of these processes occurs, maybe your objective is simply just to put another mirror here that's rigid, for example, such that we can modify the density of states. We can enhance the Stokes process, suppressing the anti-Stokes, or we can choose to do the opposite, enhance the anti-Stokes, suppressing the Stokes. And in this case, each time a photon is scattered from the pump to the anti-Stokes, you're annihilating a phonon, effectively cooling the system in the process. Okay. So the field of cavity optomechanics is immense. There's tons of brilliant science going on by a lot of brilliant researchers, huge variety of systems. This is a very dated survey, but I want to focus on our interest has been to try to figure out how to manipulate and store high frequency phonons. And this is partly because if you want to do a certain set of quantum operations, using it as a memory, for example, you'd like a few key features of a system that couples your phonons with light. You'd like it to have a decent coupling rate. You'd like it to have a nice long coherence time, and you'd also like it to be relatively protected or low thermal occupation at equilibrium, so that we have less decoherence from thermal effects. And if you can accomplish some metrics with some within your sweet spot, you can think of doing a lot of different things. And I'll say a little bit more about that later. But the question that we started to ask a while back was, first, how long can phonons live in crystals? When we cool them down, I'll say more about that. But that led us to explore larger structures. So the very successful structures for accessing gigahertz frequency phonons, which don't can have a vanishing occupation at cryogenic temperatures, has been the use of nanomechanical systems to get to, say, few gigahertz to, say, 5 or 10 gigahertz. But is there an alternative approach to accessing really high frequency phonons, maybe with systems that are more massive? And if we could, would that have some advantages? And the way that I like to think about it is this lovely quote Wolfgang Pauli made: God made the bulk, the surface was invented by the devil. So if you think of having a precious phonon bouncing around inside of some volume of material, if it's a very small volume, you're going to interact at a very high rate with the surface, as compared to a larger system that will interact much less frequently with surfaces. So perhaps you could have some advantage with respect to coherence and noise. This was our thought a long time ago. And the other question is, what are the limits of coherence? If we really did have a perfect crystal, how long could the phonons live? So what's our moonshot anyway, right? And this is where there's a lovely book by Andrew Cleland that gives a great introduction to understanding dissipation, at cryogenic temperatures, all sorts of temperatures for phonons.
Can you on Zoom?
Is there a question? So in if you think of taking, the bottom line is, if you think of taking practically any high purity crystal that's at least high purity crystal that's stoichiometric, and cooling it down, you'll find that the phonon dissipation theoretically in that crystal should really plummet to almost vanishing levels in large number of high purity materials. And that's because you're freezing out thermal phonon populations that would mediate anharmonic phonon-phonon scattering, 3-particle scattering processes that would otherwise decohere your phonons. So things get much quieter, much longer lived at low temperatures. And if you look at these beautiful ab initio papers from the 80s, you find that they suggest that single phonon lifetimes should be easily at 10 to the 10, correspond to 10 to the 10 cycles at 10 gigahertz, probably larger than that. I'm being very conservative here. So it's astronomical in theory, so it could be maybe a good memory if we do the right things. And there's a lot of evidence, when we started, there was this wonderful result by Michael Tobar, taking a centimeter scale resonator at hundreds of megahertz frequencies and showing that it can have really long lifetimes. And there's also the nanomechanical systems have got some really interesting results, super long energy storage times, but much shorter coherence times. We think it is thought that that's because of surface interactions. As we're trying to explore and answer some of these questions, what we started to do is develop a spectroscopy method. So how can we start taking something as close as possible to ideal and begin probing the phonons? We started out by taking bulk crystals and sending them to the crystal shops and asking them to polish. It didn't go so well. So we started, wrong crystal cuts, really bad surfaces, long lead times, and we thought, well, we've got to take, fate into our own hands here, So we developed this. Prash Karel developed this really neat fabrication process where we pattern a disk of photoresist, expose it to a solvent vapor environment such that it essentially forms, a dome that is atomically smooth. And then we reactive ion etch that pattern of resist, embossing it, etching it all the way, etching the way completely with reactive ion etching until we're left with this embossed in our surface. So this gives us arrays of little tiny acoustic Fabry-Perots, like seen here. And what's nice about this is with this microfabrication process, we have the ability to design the acoustic mode shapes and sizes so they match beautifully with laser beams, okay? And they support, these phonons are supported from 1 gigahertz to say hundreds of gigahertz in these structures. So it gives you a lot of latitude for studying things. So here are examples. This is some devices Prosh made in, this is a silicon device, but we can measure using Brion scattering, which is essentially acousto-optic Bragg scattering. You have a very specific set of frequencies you can talk to with Bragg scattering, coupling to traveling phonons. And in quartz, you end up talking to 12 gigahertz phonons. In silicon, you talk to 37 gigahertz. It's all about the acoustic velocity and the refractive index and phase matching. That's what determines which band of frequencies you can talk to phonons at. But this is a nice high frequency. Maybe you can reach ground state at low temperatures with that. So, but ultimately, one of the questions that we had been wondering for a long time, and Royce Luo, or Yishi Luo, in the back here now at Stanford, very happy he's in Amir's group now. So has made some really amazing inroads here. So the idea, I'm telling you a little bit about the spectroscopy approach he's pioneered. So the idea is we attach arrays of H-bars to a mirror, and we use reflection mode pump probe spectroscopy. So what we first do is shine a red laser beam in, intensity modulating it, such that electrostrictive forces will excite an elastic wave in this structure at the Bragg frequency, this Brion frequency. And then we inject a separate blue tone as a witness to observe the motion of that phonon as sidebands imprinted on this probe laser beam. So interestingly, if we vary the frequency of the drive and track the sideband, we can actually sweep out the resonances produced by these phonons inside of this acoustic Fabry-Perot. And this is the sort of thing we see. We get good at, there's a lot behind how we simulate these modes and understand the spectrum, but we're pretty good at it now after years of figuring a lot of things out. The other thing we can do is once we have this spectrum, we can choose to drive the resonator at one of these resonances and then abruptly turn off the pump. So we can witness the free induction decay of the phonons in the crystal. You can also go to low temperatures and do a lot of due diligence to see what the different origins of loss are in the crystal, making sure that Landau-Römer is not involved anymore. This is really just something that's temperature independent. So what is that temperature independent limit to the dissipation that we're observing in devices using this technique, for example? So Royce did some really amazing a lot of hard work, a lot of incredibly careful, thoughtful analysis. So what he did was take arrays of these H-bars and vary the thickness of the H-bar. So we can try to understand whether it's a surface effect or a bulk effect. Are we doing as good as we can? Have we hit the bulk limit? Or is there a surface limitation that we're facing here? And so what we see is we vary the thickness of these H-bars, or the length of these cavities, by a factor of 6, from 0.5 millimeters to 3 millimeters. What Royce has done is take each of these points is an average of measured Q value in a 3x3 array. So we get statistics. So you see the variance and the mean for each of these. And you see that follows quite nicely a constant finesse trend. So this is really a dead ringer that we are surface loss limited in these resonators. So this was really interesting. And notice that if we had some bulk contribution, we'd see this turning over like this. So this is definitely not limited by bulk losses, definitely limited by surface losses. And we're hitting Q factors of 150 million. So maybe that's suggesting we have a lot of margin. We can do a lot better. So the main thing we learned is it's all surface. So now what is the origin? Can we fix it? Can we improve the system? So at the surface, the main culprits we've been pursuing were, surface roughness induced scattering out of the acoustic mode, impurity scattering, and subsurface damage, residual structural disorder that's left through polishing of the surface. And we're pretty, all of our money's on this one. One of the reasons why is because Royce was able to fix it to a large extent, at least in one of the surfaces. So using a really cool technique, glancing angle XRD, which really does X-ray diffraction only for a very thin layer of material near the surface, he's able to see that as we polish away, incredibly carefully repolish the surface, we see that the X-ray diffraction gets much sharper. telling us that we're doing a better job of preparing the surface as we continually repolish it. So when we fix one surface, what we find is these original cues, in some cases, double, meaning that almost all of the loss when repairing one surface is removed. So this is really suggesting not only do we now have a pretty good sense for what the loss is, but how to improve it. And we think that this same structural disorder could be at play and could be problematic for maybe superconducting qubits, a lot of other things where structural disorder is known to cause TLS. So this is just, it's not maybe just this sort of problem that it affects. So anyway, we're very excited and working on, like right now, Ren Zhang is working on continuing this work along with Han Shi and Charles Ahn's group to see if we can't improve the Q. But when we did improve the Q just of one surface, we're getting to 50 million Q coherence times of about 6 milliseconds. And we see no actually dephasing. We can observe no dephasing in these devices, which is quite exciting, at least at Kelvin temperatures. Yeah.
The defect on the surface, that's from etching?
The defect.
Why is the surface so?
Oh, so we're pretty confident that, so we've taken the flat surface and repolished it. So the top surface does receive a reactive ion etch. So it's a little bit, there's another source of disorder that could, that we have identified that's slight through the etching. It's not a big effect, but the back surface was essentially pristine from the vendor, and they've done a pretty good, consistent job of polishing different substrates. So what we've done is take the original unprocessed backside of the wafer, repolish that backside, and seen a doubling in some cases of the Q as a result of that remediation. So that's because we're just doing it really careful CMP, and we're also actually monitoring. We're providing much better feedback rather than just, hey, what's my optical RMS? AFM and XRD provide a much better feedback for whether you're improving subsurface damage. So that's we don't have a machine that can control those parameters yet when in the polishing. So it's right now it's a very talented student polishing by hand. So yeah.
So if it's surface roughness, then if you go to a longer wavelength.
That's right. That's right. Sadly, so we'd like to. One of the things we're working on is electromechanically accessing these modes. The only downside of Brion is that it has a very specific spectral range unless you can tune your laser wavelength drastically. So if you go a factor of 2, well, that's a lot of expense. So we're working on electromechanically coupling to these, so we could do. No, it's really just lasers, money, modulators, all the different components you'd need in the setup, and translating that to a different wavelength. But I mean, if we had a TISAF and tunable TISAF and all the optics to go with it, maybe you could have a more uses more broadband probe. But yeah, good question. So hopeful that if we remediate both surfaces, we could be looking at Qs that are approaching 1 billion, maybe longer. And the other thing to point out, like you're saying, the frequency dependence. If you go to 5 gigahertz, if you're interested in qubits, then your coherence is going to be even larger because of that frequency dependence. So okay, so then the main question is, how can we use it? How can we access these phonons? So the big downside of a big mechanical object is your 0-point coupling is going to be much lower, right? So with nanomechanics, you can park your laser with a very low power away from resonance, and you still have enough photons to enhance your G a little bit. But in our case, we really need a very big enhancement to get to, say, megahertz coupling rates, for example. But we do that by a slightly different approach. Rather than using one cavity mode, as people typically do in cavity optomechanics, we use 2. And we separate these 2 modes by the Brion frequency so that we resonantly pump and resonantly scatter. So both are enhanced. And that allows us to really boost the coupling rates to make a large mass, make it accessible with this nested cavity optomechanical system. So and I won't go into the details. A postdoc, very talented postdoc now, Professor Hibu Yu, did a great job with this. And I'm sorry, this paper has been published in NatPhys now. But so he managed with a lot of care and a lot of tenacity to figure out this really cool method to align, to essentially select one phonon mode, the 0,0 phonon mode, coupled to it. So we see one resonance in our OMIT spectrum. We're basically using a combination of spectral filtering produced by the cavity, the optical cavity, and phase matching to help us, select only one phonon mode. And this is what he has to do: align it very precisely, painstakingly, but it works. Okay, so it's really, really exciting. So, and in using this system, once we get it all tweaked up, he's shown that if we inject a red pump wave on the red mode, and observe the anti-Stokes scattering, as we turn up the pump power, we're annihilating a phonon through this upconversion process, through the anti-Stokes scattering process, depopulating the phonon occupation of the resonator and damping it at the same time. So this is the characteristics, spectrum that you expect. This reduction and damping of the power spectrum is what you expect from when we're doing laser cooling of the phonon mode. So this is what happens as we increase the power. And the really exciting thing about this, so we managed to cool it to the ground state to point and thermal, N effective of 0.4 from 22. But the thing that I think is probably most exciting is that we don't see a deviation from this trend as we increase the pump power. And we're getting to a very high cooperativity of, in this case, 60. We're not seeing parasitic heating, which bodes well for future experiments when we're trying to do quantum operations. So that's exciting. So how would we, if we're going to build on this, how would we use this system? We can imagine quantum, generically a quantum memory, quantum repeaters, single photon sources. Doing a microwave to optical conversion is another interesting direction, but there's a lot that needs to be built up there. And just to give you an idea of what I mean by the single photon source, if we were to think of taking our cavity and initially put a burst of light in the blue mode, we would initiate a Stokes scattering process or squeezing operation. We would have spontaneous emission. If we detect a click, we know that we'll be heralding, for example, n=1 phonon Fox state inside of the acoustic resonator, and it can stay in the resonator until within the coherence time, until which time we inject a red wave, which implements a beam splitter operation or readout, up converting the photon. So we can think of this as being a heralded single photon source, if you like. How might you use this? So Maggie Pavlovich and Shruti Puri's group has worked out a very nice analysis of a system, really a system analysis, showing that if we were to have a parallel array of these heralded single photon sources and we were to choose to release them, the n=1 Fox state at the same time, you've got quite a resource state that you can produce. At the same time, she's showing that you can use this acoustic quantum memory to implement entanglement and actually to start doing things like building your cluster states or something, in this system. So there's a lot of interesting possibilities. And I just want to, start by, as I move on to the next topic, I just want to be sure to acknowledge in red all the folks who did a lot of, the heavy lifting of the data that I've shown here, as well as Jack Harris and Rob Shulkoff, long-time colleagues and collaborators on this work. So they're the ones that did the hard work. So the thing that I want to say, though, is, okay, I painted this picture for arrays of cavities. Boy, it was hard to get that one cavity aligned. We did it. But how might we scale this up? And this is where we start talking about technology and micromirrors. So I'll tell you in a minute about, we adapted this fabrication technique that I showed you for these acoustic resonators to make arrays of mirrors that yield nice high finesse. And we've also developed strategies to bond these mirror arrays together in non-trivial geometries, something like a sandwich like this. So we're thinking of, maybe we could make arrays no longer have to painstakingly align the H-bar center, the center of the acoustic resonator to the optical resonator, if we use alignment features, bonding together at the wafer level, dicing up. Then you could maybe have identical copies of these single photon sources if that's where we decide to go. So that's the sort of thing we're thinking of and where we're headed. But so maybe this is a switch of topic here now. I want to tell you about some of the micromirror and microcavity technologies that we've been working on over the last 6 years. So as I mentioned, this is the first generation. We've gone on to many different improved and different fab techniques, but I'll show you how we landed at this first fabrication process from the resonator fab. So, so if we wanted to make a mirror, clearly we want a concave surface to deposit Ramin's amazing coatings on. And so what we start out with when we're making these acoustic resonators was we take our disk of resist, we expose it to solvent vapor environment, causing mobility, producing mobility in the resist. If we keep going and going and going, the terminal shape is a dome. But intermediate shapes determined by surface tension actually have a concave shape. And that is reconfigurable by changing the initial shape of your resist. So, so if we halt this reflow here, and then we do this pattern transfer, we end up with these dimples or concave surfaces where we can actually vary the radius of curvature quite dramatically in these systems. The thing that I found shocking is that we can take a super polished substrate with half angstrom roughness, etch. If we do it very carefully, we don't add any roughness. In fact, at some spectral components, we're dropping the roughness just a little. So that was a really shocking thing for me. Okay, so how does this work? So we coat these amazing, we put this amazing multi-layer stack down with Ramin, and we're measuring small ROC 4 millimeter and large ROC mirrors of 1 meter with finesse exceeding 1 million. So, and these are a scatter plot showing the different finesse measurements with different ROCs that we've put across different wafers. And really, until my grad student gets tired, there's a lot of measurements here. So, so this allows us to make on a wafer arrays of cavities. Okay, and before I go on talking about this technique, I find it useful to just pause for a moment and say, why are, if we're going to do all this hard work of integrating and creating new types of resonators, little microfabry pros, and trying to have technological impact, pausing for a moment and asking, what are the really essential ways that Fabry Pros are better or different from ring resonators or other sort of integrated resonators that we might choose to use? And there's a couple of things that we keep coming back to. One is atoms love to live in vacuum. And so atom photon coupling, really, Fabry Pros seems like one of the best tools to enable that, if you want to do strong coupling, for example. The other application we keep returning to is making very stable oscillators. So I'll tell you a little bit about vacuum gap reference cavities, but the idea is that instead of having your electromagnetic mode live in a dielectric where there are thermodynamic fluctuations that will actually cause the mode to jitter around, if you store the energy almost entirely in vacuum, you're really largely immune from those material degrees of freedom that would cause fluctuations in phase noise and other things. So, stable reference cavities are the place where we first got funding to really start pushing in this direction. But we are now returning to the problems of atomic, control. So, so just as a little bit of background, I don't know if everybody knows here, but if you go to NIST, if you go to a huge number of atomic physics labs, anybody making clocks, you're going to see a lot of reference cavities. So these are really amazing. This is an amazing technology that's a laboratory scale kind of thing. Usually some sort of a vacuum system that's low noise, low vibration, and a handcrafted, two super mirrors attached to a very special spacer made out of ultra low expansion glass that has a 0 thermal expansion at some temperature, usually 25, 30 degrees C, something like that, such that this produces an incredibly stable resonator because the energy is stored in vacuum. So this is an amazing technology. It's really how it is that the world's best clocks and oscillators are made in laboratories around the world. So, the question that we were posing, along with Scott Diddams and Frank Quinlan at NIST, who turned out to be really fabulous research collaborators in all of this, was can we take the advantages of these vacuum gap resonators, their stability and low noise, and can we somehow make that capability, shrink it down to a small device so that we can have portable clock technologies, or maybe more scalable atomic sources, all kinds of different things. So the idea was we fabricate these relatively large radius of curvature mirrors on a 3x3 array. In this example, we bond them together with a ULE spacer that has boreholes. So there's actually vacuum between the two mirrors, the curved mirror and the flat mirror. So we bond these together in vacuum, dice it up, so that we actually have many, arrays of standalone reference cavities that no longer require this big vacuum system because we've bonded them together in vacuum. In this case, we've done 3 millimeter and 4 millimeter so far. So something like 30, 40 gigahertz. And these, with their nice high finesses, we're getting, typically Qs in the billions. And at ADEV so far, we've achieved around 2 times 10 to the minus 14. Frank Quinlan's team has shown that. Allen deviation, sorry. So that's telling you about the frequency fluctuation, center frequency fluctuations over time. So yeah, and so okay, won't get too far into it, but the two things that we were supported to do, one was making compact reference cavities for portable atomic clocks, but more recently we've been supported to actually make photonically enabled microwave sources, microwave oscillators. And the idea here is not too complicated. It's if you can make a very, very clean, low noise laser oscillator that's oscillating at 200 terahertz, for example, at 1550 wavelengths, if we can use optical frequency division to take that low phase noise and divide it down, the phase noise will go up. If you drop the frequency by a factor of 10, you get 20 log reduction in the phase noise. So if you go down even further, so you go down to 10 gigahertz, suddenly you have this really massive reduction in noise. And what we really want to do, so many of us really want to see photonics finally displace, entrenched technologies like microwave crystal oscillators or something like that. So that would be, if I could do that before I die, that would be kind of awesome. Or help, or make. I can't do it, meaning be a part of it. That would be great. But anyway, so along the way, we made these little reference cavities to try to enable that, and also develop new strategies to integrate these cavities with photonic circuits. So that's what I'll tell you about briefly, and then wrap up here. So many of you may know, cavities. If you want to stabilize your laser to a cavity, one of the best tools is pound-river Hall locking. The idea is we phase modulate a laser, we reflect it off of the cavity, and upon reflection, the response of the cavity turns our phase modulation into an intensity modulation. So if we demodulate that intensity modulation properly, we get an error signal with a unique, a 0, where the cavity is on resonance with the laser. And that's a really powerful technique. So what we've been working on is implementing that in a photonic circuit so that we can have pound-river Hall locking and other sorts of locking techniques in an integrated compact system. And so one of the challenges is actually just interfacing the cavity to the circuit. Most of the time, we've been interfacing ring resonators on photonic circuits. These are traveling wave devices. This is a standing wave device. And we don't have isolators and circulators in integrated photonics. So, but there is a really cool technique many of you here are using called I've known it as the poor man's isolator, quarter wave plate and PBS. You can put light in one port, it gets reflected, goes out the other port, right? So that allows us to take all of the laser power, our precious photons that we're interrogating the cavity with, and detect them. So to do the same thing, we have used inverse design, this amazing technique, to design a vertical emission grating coupler that takes the place of our polarizing beam splitter. Okay, so it has each port maps to a polarization. So light coming in this way maps to this polarization, light coming this way maps to this polarization. So when we pass light through this Mach center interferometer with a tunable phase, one of these arms is experiencing a pi/2 phase shift, just like you would get with a quarter wave plate. So you have circularly polarized light, hits the cavity, comes back, all the light comes out of port 2 that came into port 1. Okay, just like we have in the poor man's eye. So it is exact mapping of the poor man's isolator from free space in a circuit diagram. So this actually works. The inverse design grating coupler, really neat. Shocking to me how well it works. We get 60% efficiency, in the vertical direction, and coupling into a single mode fiber that we use as our proxy for our cavity. And then we use a Grin lens that focuses the same spot size, transforms this, into our cavity mode that's 250 microns in this case, for our reference cavity. And this works very well. So we get, in sending light in port 1 of the circuit, we have, around 3 dB loss each pass, each time we go into the cavity and out. So that gives us about 7 dB all said and done for loss coming out of this port 2 of the poor man's isolator. So hey, it's working, and we can see the dip. Sorry, our laser couldn't sweep slowly enough, the one we're using here, so it looks like a ringing response instead of nice, beautiful Lorentzian, but it is a beautiful Lorentzian. So anyway, that works. That was kind of neat. The other thing we've done is actually implement something called self-injection locking with our cavities. So here we have a distributed feedback laser and a special circuit that Haotian Cheng has designed and developed that transforms the response of the resonator. Typically, when you're looking at the reflection of a Fabry-Perot, you see an anti-resonance or a dip when you're on resonance with your cavity mode. But what we want to do in order to create positive feedback into our DFB laser is we would like to transform that dip in reflection response into a peak, something that looks much more like the transmission through your Fabry-Perot, such that we can implement feedback into the laser, stabilizing and locking the laser to the frequency of the cavity. So that's just what we've done. And when we do that, the DFB has a dramatic line narrowing and inherits the frequency stability of the reference cavity. So we see pretty darn impressive phase noise. At least as a time of publication, this was the best for sort of a compact system of this size. And really, some of the limitations at low frequencies were just because we didn't have it packaged. So we're doing much better now with our latest experiments. But we get some pretty dramatic, something like 60 dB of phase noise suppression from the initial laser phase noise, and a very a really impressive little compact laser out of this. So okay, just summarizing, we started out with acoustic resonators. We saw that we could laser cool these guys, these phonon modes and these H bars to work our way towards some form of quantum control. And we've also explored new technologies that we could enable with these cavities. But I'd be very interested to hear what interests people, what people are thinking of, if there are crazy things or cool things we could do or work on together. Be happy to discuss it. And last but not least, I want to thank our collaborators at NIST and C Boulder, UCSB. A lot of the device development and was done jointly with them. So, and thanks very much.
Thanks, Peter. We have time for a couple of questions. So I guess you said you can shape the
Yeah. So I haven't shown you some of my group members have really done a great job of developing a grayscale fabrication technique. So you're really coming awfully close to the final. So one of the downsides of the approach that I showed you is it relies on exposing the resist to the solvent for a long period of time, and that requires a lot of motion of the resist to reshape it. And it's how well that works varies quite a bit, batch to batch, age of the resist. So there's some varying parameters. We have a hard time getting the same result every time. There's always a little bit of playing and fiddling every time we do the process. So the grayscale, where you're varying exposure level to develop and get a pattern that's much closer to your final shape, gives you a huge amount of versatility. We can literally make not quite arbitrary, but pretty close to arbitrary mirror shapes with this, and then we just do a finishing step at the end. So that's kind of what we're doing right now. But yeah, does that? Yeah.
Sorry, we'll stick to the microphone as much as we can for the Zoom audience. So.
Yeah, a lot of great stuff. Just one detail: how this circuit that transforms the dip into a peak, how does that work?
Oh yes. So yeah, let's go back there. So the idea is, the way to think about it is, let's say your laser light, the response that is produced in reflection by the resonator is going to have a dip response at first. So really, what's going on here is we're taking half of the light, it's hitting the cavity, the other half is going through. This is basically is being reflected off of. So you can think of this as being like a Michelson. This is a Michelson interferometer here. This is essentially, this is a mirror, a loop mirror. So basically, when these two combine, provided the phase of the light coming from the loop mirror is correct, we can actually cancel the background, unity reflection off resonance. And that leaves us with really the resonant response that you would get in transmission. So it's really, we're just subtracting part of the component of the field that's canceling the component of the field that would otherwise give you a unity background reflection. But yeah, it's kind of fun. It's wild, right? So yeah.
Yeah, I guess. Oh, sorry.
Oh,
You all put your hands down. I have the microphone. So this is really fun stuff. So I guess two questions, like what sets the dimension limits for these lenses? You had a certain, value for the radius of curvature and for the size of the lens.
So I'd say the biggest limitation. So the radius of curvature can go from 100 microns up to meters. The biggest limitation, I would say, practical limit, is the etch depth. So meaning making a really big mirror sag. That's something we can't do. So making the mirror depth more than a couple, 2-3 microns would be kind of hard because we have to do this incredibly careful, slow etch. And we'd be using a tool that heavily used tool, most heavily used tool for, we're already etching close to an hour. And usually people are doing like 5-minute etches in the fab. So we're hogging it quite a bit.
All right, let's just talk about hogging it. I'll ask another question. So you talked about the surface damage that was affecting the acoustic waves.
Yeah.
Is there any reason to believe that would affect the optical properties of the mirror on reflection?
Optical properties of the mirror. I guess usually that subsurface damage is well below the mirror stack if you're thinking of a cavity that's formed in vacuum, for example. So it's not impossible that there could be some excess noise, mechanical noise or something. If you're thinking of, thermal mechanical noise or other things, yeah, maybe it could be doing something. And maybe even more something at low temperatures or something. I'm not sure. If you've got TLS, who knows? But yeah, it's a good question. And I'm also curious to know if, so there's a lot that's been studied about polishing and subsurface damage for laser damage and laser ablation. And I wanted to see if we can connect the two, see if the techniques from one field can help the other, that kind of thing. But we're still looking for better ways to assess damage. Yeah.
Yeah, great talk. Two quick questions. How small of diameter can you make the mirrors? And in terms of the phonon materials, do you do any thermal annealing afterwards?
So those are interesting questions. So smallest diameter, I've talked to my students, and I think they've done down to 100 micron. We think shouldn't be too bad. So as the diameter of the mirror. So for really small ROC mirrors, that should work well. For the so wait, what the second question was? Annealing. Yes. Yeah. So quartz is a sticky one. Quartz is tricky, and there's some subtlety here. So quartz has a phase transition. And Royce, he's your resident expert. You can always talk more with him. But quartz has a phase transition from alpha phase crystal to beta at 570 something degrees, and that really makes it very hard for us to do the same tricks you might do in diamond. At the same time, like or sapphire or other materials where you do restructure the surface, recrystallize. At the same time, the recrystallization of the surface will actually make bumps. And it will also make the surface non-planar. So we're stuck. It's a tough one. And that's why, yeah. There's things that are relaxing and changing. So yeah, don't know. It's a good question. Yeah.
More questions? Do you have questions?
Thank you. Very fantastic talk. I have a lot of questions. So I think my first question is about your pump probe spectroscopy. So actually, I think you should one slide say that there's angle dependence. It will actually induce a lot of modes. So and also you have a second laser. I was wondering how tolerable are these cavity, to those second laser without introducing some unwanted acoustic modes.
So I'm not entirely sure I follow. So you're saying you're wondering whether laser one. So yeah, could you rephrase that again?
Yeah. So basically, actually, when we shine these free space lasers, the palm probe lasers, sometimes in reality you have some like misalignment,
Okay,
whatever.
sure.
So
I mean, I think the expert to explain that would be right next to you.
yeah, we can talk offline. Yeah. Okay. So my second question is about your single photon emission. Should I picture that as some like a single photon emission instead?
I mean, so the one way to think about it is, if you know what pair generation is in optics, so you take a blue photon, split it into two red photons. In our acoustic system through a Raman process, you have a redshifted photon and you've got a signal that's your redshifted photon and your idler that is the phonon. So they're really playing the exact same role in that three particle interaction. Does that help?
Yeah, thank you.
Okay, great.